Hello, Chem 112. It's me again. Just wanted to introduce you guys to some stoichiometry, and I can feel already you guys are probably vomiting in your kitchen or in your living room or wherever you are watching this. Not a very fun subject, but unfortunately it's something that we really have to understand. One of the things that students don't always like about it is there's a lot of arithmetic in it. And if it turns out, if you just kind of understand ratios and things like that, you're always going to be able to find the answer. Another thing which I like to do is talk about the why, which was never told to me when I first learned this stuff. Kind of why do we have to talk about all this crazy mole stuff that we're getting to? So the first thing to keep in mind about stoichiometry is that it's kind of thought about as almost kind of a way to use a recipe for a chemical reaction, right? And so we talked about balanced chemical reactions, and I kind of just picked one out at random over here. And in this particular one, you can see hydrogen gas reacting with tungsten, which is a W, to form this thing called tungsten hydride. We don't really care about this reaction, but I kind of wanted to show you a couple of ins and outs of stoichiometry here along the way before we just become mindless calculating automatons having to do with moles and all that other kind of crazy stuff. So one of the first things to notice is that I had to balance this reaction with a 2 for a coefficient in front of the hydrogen. And I have talked about before how that ratio has to be maintained, right? The fact that if I want to make that tungsten hydride over there, that I have to make sure that I've got twice as much this as that. But the problem is that all these chemical substances, they all weigh different things. So in this particular reaction, right, you might think that if you had to go measure stuff out on a balance, that, you know, you would have to weigh twice as much of this, right, twice the mass of that relative to that. Turns out that is wrong. And I've kind of picked out a couple of things from around the house here to kind of represent why that would be wrong. So let's imagine that this hydrogen gas, right, is actually these two little ping pong balls right here. Right, so there's my hydrogen gas. You notice they're like nice and light, right? Well, let's pretend that tungsten is this medicine ball, right? What would happen if we measured out, you know, twice the mass of those hydrogen ping pong balls relative to this? That would be a freaking ridiculous amount of hydrogen. So it turns out that these ratios that we have to maintain have nothing to do with mass. I shouldn't say it has nothing to do with mass, but what is true is that it is not a true statement to say that you need twice the mass of this to react with that particular tungsten right there. But what is true is that the overall number of molecules are told to us by these coefficients in the reaction, right? I gotta put this thing down. Whew, I'm starting to sweat. Don't want a sweaty mullet, for God's sake. So we got these two hydrogens, right? These two hydrogen ping pong balls, right? You can imagine, you know, two of these guys have to kind of get together with one of these gigantic, you know, medicine balls right here. So these are not in terms of mass. They are in terms of actual numbers of molecules. Okay, but the problem is that in chemistry class, how do you actually measure the stuff out? Well, you use the masses. You throw it on a balance, right? So we need some way to kind of take this like mass information and convert it into the actual number of molecules. And that's where we've come up with this as chemists, this really confusing concept known as the number of moles of something. As I introduce this concept of the mole, it is important to recognize is all it is a number. It's a flippin' huge number. So you probably have been in like the bakery before and ordered a dozen donuts, right? You said, hey, go get me a dozen donuts, right? And how many did they bring out? Well, 12, and then they think the baker's done it in 13 or some craziness like that. I don't understand that system. I'm a diabetic, so I don't eat too many donuts. But just like you had to say, hey, go get me a dozen donuts, it wouldn't make sense for you to say, go get me a dozen, because the person would look at you and say, yeah, a dozen what? Do you want 12 donuts? Or do you want, 12 I don't know, popsicle sticks or something like that, right? So it's important that when you talk about this concept of the mole, all it is a number, first of all. Second of all, make sure that you're always considering mole of what, right? Just like we have to think about, okay, I know a dozen is 12, but a dozen of what, right? Usually it's donuts. Good. So what is true of all of these numbers? I could say that in this reaction, the stoichiometry of this reaction is such that I need 2 molecules of this to react with 1 atom of that, right? That's what those numbers are telling me. Well, it turns out that if I wanted to use a dozen now, that would also make sense. I could say I need 2 dozen of these hydrogen molecules and 1 dozen of those tungsten atoms in order to form 1 dozen of those tungsten hydrides there, right? And so that dozen, if I said a dozen, it probably wouldn't make you confused, right? Because we all know that a dozen is just 12, and I'm just maintaining that same ratio as I went through, right? If I actually could count these out and I said, hey, go get me 2 dozen of those things, you would count out 24 hydrogens, right? And then I said, go get me a dozen of those, you count out 12 of those medicine balls, and then we'd go off to the races, we'd do the chemical reaction. Well, it turns out that that number, which we call a mole, is huge. So I'm going to write it down just so that you can see it kind of for the first time. When I say I need you to go get me 1 mole of something, I am talking about this number of somethings. That, my friends, is a gigantic number, right? 6 with essentially 22 zeros after it of things. That's a huge number, this thing right here. But the thing is most of the time when you're talking about this huge number, you're talking about a huge number of molecules, which are these itsy-bitsy little tiny things, right? And so that is just a number, like a 12, a dozen is 12, a mole is that, right? I sometimes call this the chemist's dozen. So I don't want this to be a confusing factor for you. A lot of times when students have to use this number, things get really confusing. They start doing all kinds of crazy dimensional analysis steps and stuff like that. In this class, especially in its shortened nature, we're going to kind of know this number, right? That we know that a mole is huge, but we're not going to really calculate or refer to it that often, maybe occasionally, right? What we need to know is this really spectacular thing that happens on the periodic table, right? It turns out that every single thing on the periodic table, if you look at that atomic mass that we've talked about before, right? The average of all naturally occurring isotopes, blah, 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 right? That decimal number on the periodic table, it turns out that also tells you the number of grams you need to measure out on a balance to get exactly 1 mole of that thing. Right? And so if we went back to this reaction, right? And let's say that I wanted to measure out a mole of tungsten atoms. Okay, so I looked up that number on the periodic table. It turns out that when you look at tungsten, find it on the periodic table, you'll see that atomic mass that's listed right out. And it says, I think, 183.84, right? Back in the days when we were talking about about atomic structure, that was in that unit called atomic mass units, right? And so that atomic mass unit kind of isn't really what we're talking about right now. But the way that we've defined all these atomic masses brilliantly on the periodic table, it turns out that that atomic mass right there can also have units of grams per mole. There is a derived unit that tells me exactly how many grams are in 1 mole of tungsten. So if I'm faced with this conundrum and I have to figure out, I have to put on the balance exactly 1 mole of tungsten, right? I know in my head that I've got a whole ton of atoms of tungsten, right? Like a 6.02 times 10 to the 23rd, right? That equals 1 mole of tungsten. But I can't go into lab and count, 1, 2, 3, 4 up to that number, right? What I'm going to do instead is I'm going to make my life a lot easier. I'm going to measure out exactly 183.84 grams of tungsten. And it turns out that if I measure out that amount, that's a perfect number of moles of tungsten. And I would come over here and I would do the exact same thing. I would say, well, I know I need H2, right? And I would calculate what's called the formula mass, otherwise known as the molar mass of H2. What would you do? Well, to figure out the molar mass of this thing, you just take two atomic masses for hydrogen, add them together, and there you go, right? And so hold on just a second, I'll do that for you. So I've set up the calculation for the molar mass of H2, and what we're gonna do is we know that there are two hydrogens that are a part of that thing. So I plugged in 2 there. I'm gonna take 2 times the atomic mass of hydrogen that I find on the periodic table. And so I did that right down here. Hopefully you can see it. I'm not so sure you can see it on the video. Hopefully you can. But 2 times that 1.01 grams per mole. This I rounded to. In this class, usually when we do formula masses, also called molar masses, usually what you're going to do is you're going to round to 2 decimal points. There are rules for it, but we're not going to really go too in-depth into that. So once you've done that calculation and that number you ended up with, right, we now know that if I want 1 mole of hydrogen gas, of H2, I need to measure out on a balance 2.20 grams, right? So that would be 1 mole. Here, this is telling me I need 2 moles. So you probably guessed that you would take that number, multiply it by 2. That's the number of grams you would use, right? And so that's kind of where we're going to go as we kind of work our way through the madness of this stoichiometry. Those 2 concepts are central, though. You really have to understand, first of all, that these are a ratio that must be maintained, those coefficients. So we kind of have that balancing chemical reaction things floating around in our brain. Another thing which you have to be able to understand is that different elements will weigh different things, and we have to know how to look up masses on the periodic table to figure out how many grams are actually 1 mole of that thing, right? And so what we're going to have to do is then take that information and somehow use it to figure out how to properly do chemical reactions. So that's what the next several videos will be about. I will show you how to calculate some slightly harder molar masses. By the way, I should say that chemists love to call things by 7,000 different things that mean the same. So I'm going to do my best to call this molar mass. It kind of makes sense because it's always the mass in 1 mole of something. But you'll definitely see atomic mass, atomic weight, formula mass, molecular weight, molecular mass, like all kinds of different things. I'm going to do my darndest to really try hard to just use molar mass for the name of this thing. They also call it formula mass. I think I said that already. Who knows? But anyway, you get the point, right? This is kind of ultimately where we want to be able to go. Next video, I'm going to show you how to use dimensional analysis, our old friend, to calculate, use that molar mass info to do some different calculations. And then I'll show you some good ways to kind of handle the stoichiometry here when the coefficients get really weird. So keep watching.